again, everybody. In this video we're going to pick up where we left off with the Swedish Landlords study, and we'll show you how to write hypotheses and find a p-value to test whether the name makes a difference among the population of all landlords or not. We'll show you how to find a p-value using a randomization test, and we'll let you read about the StatCrunch 2 sample test for proportions at another time. In this example, we're only going to compare the applications signed by Eva and those signed by Eric. The methods we're learning right now can only be used for directly comparing two groups at a time, so we'll ignore the Fatima and Ahmed data for the time being. Before we begin, let's be sure we understand what's at stake. We already saw a difference in the samples, but we must determine whether this difference is statistically significant. That is it large enough to rule out sampling variability as the reason for the difference? It's important to note that the researchers decided to find an answer to this question before they ever sent out one single application. This was one of the questions their experiment was designed to answer. They didn't come up with a question after they saw the data. That's called cherry picking, and it would be considered unethical at best. Back to the study. Here's the question that we're trying to answer. Is there evidence of discrimination in the housing market? Notice that there are two percentages we want to learn about. Pi with the subscript Eva we'll reserve for the success rate when the applications are signed by Eva, but notice there's no hat. That means we're talking about the percentage among the population of all landlords. These landlords are going to be represented by the sample of 303 who received an actual application, but these landlords are represented by the sample of 303 who received an actual application, but they are representing a much larger population. Similarly, there's another percentage, and that's the success rate represented by Eric's applications. We'll compare the two treatments for the population of all landlords. The null hypothesis is that these two proportions are the same for the population of all landlords. That is, there's no difference in the overall success rates. The alternative hypothesis is that there is a difference, and in this case we chose a two-sided hypothesis because we had no prior information about discrimination except maybe for some personal hunch. Here's the data in the form of the contingency table and the bar graph. We remind you of what we said last time. It sure looks like there's an association between the variables. The success rate for the percentages we found last time, 19.8% for Eva and 10.5% for Eric, these give us a difference of about 9.3% between the two. It is kind of hard to believe that a difference as big as this one for Eva and Eric could happen by chance alone, but we really do need a p-value before we can know for sure. Here's how we get a p-value. It's through a new kind of sampling distribution that comes from a randomization test. We'll show you how to use StatCrunch to set up the applet first, and then we'll explain the logic of the test right before we find the p-value. In StatCrunch, we click on Applets, and then Resampling, and choose the randomization test for two proportions. We'll scroll down in the window until we find the From Summary box, and then we'll enter the data 60 out of 303 for Eric, and 32 out of, that was for Eva, and 32 out of 304 for Eric, and then we'll push Compute. The order that we entered for Eva and Eric really doesn't matter. Now here's what the applet will do. It will take the results for all of the 607 landlords in the experiment, and it'll randomly assign their results, whether they accept or reject the application, to one of two groups. We can do this many, many times, and we'll record the differences in percentages each time. In this way, we can find out whether a difference like the one in the sample, the 9.3% difference, is likely to occur by chance alone. That is, we can find out whether the experimental results could reasonably be predicted by the null hypothesis, or whether there must be something else going on. Notice that now the applet is all set to count how many times a certain number is more extreme than 9.3%, whether positive or negative. What does this mean? As in all significance tests, we begin by assuming the null hypothesis is true, and then we ask, what if there really is no discrimination and the name on the application makes no difference? If this is right, then the landlords accepted or rejected the applications. The landlords who accepted or rejected the applications would have done so based on the application itself and had nothing to do with the name on it. The same is true for the applications that were rejected. So there are a total of 607 landlords in our experiment, if we ignore, of course, Fatima and Ahmed's data. And of these, we assume that 92 landlords were going to accept the application regardless of the name on it. 92 from the 60 plus 32 in the two groups. Then why is there a discrepancy in the two groups' percentages? Well, maybe it was sheer luck. But then if it was, we should be able to recreate such luck by doing a randomization test. As we said earlier, the applet will randomly shuffle these applications over and over again to find out just how likely it is to get a difference at least as large as the one we saw in the actual experiment, the 9.3%. Let's proceed. When we click one time, we see a random shuffling and a difference of close to 6% for these two proportions. This is the difference in success rates in the two random groups, and it's recorded on the graph. We can repeat this several times. Each time, the computer reshuffles the application to see what kinds of differences are common when only randomness is at play. Each time, the computer records the difference and whether it's larger than 9.3% or not. So far, none of the three have, but let's skip ahead and do this several thousand times. After more than 5,000 randomizations on the application, we observed a difference at least as large as the 9.3% difference in the experiment only a few times, in fact 7 times. Note the number in the lower right-hand corner of the table in red. This number is the p-value, or at least an approximation of the p-value. A difference as big as the one in the experiment occurred only 7 times in 5,000 or so simulations, or about 0.14% of the time. Since it was so rare to duplicate the experimental result in our randomization test, we know that such a difference in success rates must be unlikely to occur by chance. There must be something else besides chance going on. So we record that the difference was statistically significant. Remember, the evidence is the p-value. Therefore, we have very strong evidence against the null hypothesis, and so we reject it. At least for the ethnic Swedish applicants, we've detected that there's an association between the gender of the applicant and the success of the application. Now we want to ask about causality. Is the observed difference in success rates likely to be caused by the gender of the applicant? Or is the difference merely a coincidence, not accidental, but requiring some other explanation besides the association we noticed? So we ask these questions. Was it a randomized experiment? Was there a legitimate comparison group? Were all the conditions kept the same for each group? Were the subjects blinded? Since we can answer yes to all 3 questions, the experimental design accounts for lurking variables. Any naturally occurring lurking variables would have been balanced between the 2 groups and so cannot be responsible for the differences that we see. Then what is? It must be the names written on the applications. After all, this is the only difference between the groups. In other words, when we combine the evidence of the p-value together with the careful design of the study, we have compelling evidence that there is discrimination in the Swedish system. Not only is the difference we observed not explainable by sampling variability, but no lurking variables can explain it either. The conclusion is the strongest kind possible. The association's causal. Gender causes discrimination among landlords in the population, at least in the kinds of rental applications and processes being considered here. For any 2-sample test like this one, be sure you tell everyone about these 4 items. I remember them as HPAC, like a hypothesis package. First, write hypotheses to be tested. Then gather data and use it to find a p-value. The p-value is what helps us to determine if the variables are associated or not, so we're looking for statistical significance. Remember that associated in this context means we have ruled out chance as the reason for the difference in proportions. It wasn't just a lucky sample. Finally, if there is an association, and only if there is an association, then consider the study design to see if you can draw a causal conclusion. Actually, you would have seen this coming even when you designed your study. If it's someone else's study, it's a very important point to keep in mind. Causal conclusions tell us something about how things are related and perhaps how to change them to get a better outcome. Well, there you have it. We'll let you read about the other ways to find a p-value using StatCrunch and some of the other details in your book. If you have any questions, please let me know.